Let's move on to our last long speaker for today. He's Mark Nottingham, and his talk is the Apollo 12 Regolith Basalt Noble Gas Systematics Implications for Future Exploration. Take it away, Mark.
Hi everyone, I'm Mark Nottingham from the University of Manchester, and today I'll be talking about a study that was a collaboration between the University of Manchester, Birkbeck College London, and the Scottish University's Environmental Research Centre. There we go. So in the study, we use noble gases derived from individual lunar regolith soil fragments to understand the evolution and impact history of the Apollo 12 landing site by modelling two-stage cosmic ray exposure histories. And to do this, we use neon isotopes and sample-specific bulk chemistry measurements to first constrain the concentrations of neon components present in the gas inventory of each basalt grain, and second, to constrain the cosmogenic gases into production in one of two stages of cosmic ray exposure, with each stage occurring under distinct burial conditions. But first, it's kind of important to understand just how complex noble gas inventories in lunar samples can be. The figure on the right here shows a number of the processes that all affect the lunar regolith to varying degrees. Untangling these processes from each other can be quite difficult. Of particular interest in our study were cosmic rays and the spallation reactions that they cause. So for anyone that doesn't know, the surface of the moon, because it doesn't have an atmosphere or a magnetic field, it's continuously exposed to spaceborne radiation that's collectively called cosmic rays. This radiation flux triggers nuclear spallation reactions within rocks on the lunar surface, and the cosmic rays are broadly divided into two groups based on their origin. So those that originate from the sun are called solar cosmic rays, or SCRs, and they're generally lower energy than their galactic cosmic ray counterparts, or GCRs, which originate from outside of the solar system from sources such as supernova. Importantly, solar cosmic rays only penetrate a few centimeters into the regolith before they're totally attenuated, whereas galactic cosmic rays penetrate to beyond a meter's depth. The rate of production of each isotope depends primarily on shielding or burial depth and the sample chemistry. And importantly for neon isotopes, the production rate ratios between each isotope don't stay constant with a changing depth. This means that if we can isolate the solar cosmic ray produced isotopes from the galactic cosmic ray produced isotopes, they can act as a good indicator of the sample's near surface residency duration. This study examines samples from the Apollo 12 landing site on the southeastern side of the Oceanus Procellarum. Over its history, the site is thought to have had contributions of ejecta from impacts that formed craters like Copernicus, Reinhold, and the Landsberg craters. And subsequently, impacts that formed several smaller named and unnamed craters have reworked the regolith cover that's local to the landing site. The samples we used in the study were 9 individual basalt fragments from parent soil 12003, and they represent a range of different basalt lithologies local to the area. Each soil grain was split into 2 pieces, with one being used to determine the sample chemistry in work published by Alexander et al. And Snape et al. And the remaining piece of the divided grain was then analysed for its noble gas contents. Before working out the cosmic ray exposure history of the sample, we first have to partition the measured gas into its constituent components. However, our method requires this partitioning to be done without the use of assumed end member component compositions. That's to say the measurements alone have to inform the partitioning rather than the more conventional literature approach, where you would assume end member compositions. To do this, we collect measurements of gases released in temperature step intervals and then model an unconstrained mixing line representing a binary mixture of implanted solar wind and cosmogenic gases that dominate the gas inventory of each sample. We then reduce Mahalanobis distance of each measurement to basically get the line to fit the data, the modeled line to fit the data as best as it can. That modeled line is assumed to be an accurate representation of this binary gas mix within the sample. And through that, we can then calculate a gas fraction representative of those gases produced by spallation reactions. So for our model, we adopt theoretical cosmogenic nuclide production rate, the cosmogenic production rate model published by Hohenberg et al. Because it provides both solar and galactic cosmic ray spallation production rates. The depth-dependent production rate profile for each isotope is unique, so taking each of those isotopes and combining them into a 3-isotope plot gives us a plot similar to the one that I'm showing here. Just for your information, the numbers on the curve are shielding depths in grams per square centimeter. Given this depth dependence, we can divide the curve into 2 sections, one representative of the sample being buried within 5 grams per square centimeter of the lunar surface in the yellow double line, and one representing deeper burial between 5 and 500 grams per square centimeter in the blue solid line. If we have a sample buried at 65 grams per square centimeter in the regolith, and then any cosmogenic neon produced will show an isotopic composition represented by that red circle that's now plotted on the graph. And if we exhume our theoretical sample from that depth to within 5 centimeters of the lunar surface, where many Apollo samples were collected from, we change the ratios of the cosmogenic gas production so that any gas produced at the surface will now conform to this new composition. And given our samples were collected from the lunar surface, we can assume that they were exposed at the surface for at least part of their existence. Therefore, working in reverse, if we anchor one stage of exposure at the lunar surface and extrapolate a line, that green dashed line, from the value back through the calculated cosmogenic end member value, then the intercept of that line gives us the theoretical production rates at the depth and the shielding depth itself. Our results for the 2-stage models were quite promising. 3 samples showed surface exposure of 6 to 7 million years plus or minus 2. And 4 samples only showed deeply shielded exposure, which means that their surface exposure was at most a few 100,000 years, so below the resolution we can resolve to. 2 samples had mixing lines and cosmogenic end members that didn't fall within the calculated production rate curve, and this likely means there was significant mineralogical difference between the aliquot that is used for the chemistry analyses and the aliquot that was used for noble gas analysis. However, we also can't rule out that these samples were buried deeper than the Hohenberg model is calibrated for. These samples all seem to have been excavated to the surface relatively recently, possibly by an impact such as the one that formed Sharp Crater, which was reported as having an age lower than 10 million years. Those samples with no discernible surface exposure likely derived from one of the recent smaller unnamed crater formation impacts. Our results fall between the ages reported by Bandari et al., and we surmise that the slightly longer surface exposure age that we calculate is a result of our surface exposure model not accounting for depth, not accounting for the depth being between 0 and 5 grams per square centimeter. It's also possible this is due to rapid reworking of the surface regolith cover, which would be in keeping with the findings of Costello et al. We believe these samples can best be explained by a long period of burial beyond the depth cosmic rays can penetrate to, followed by exhumation by impacts that formed either surveyor or head craters, to a depth where cosmogenic nuclide accumulation could occur, and then followed by excavation to the surface by either an impact that formed Sharp crater or one of the unnamed craters around the landing site. And because I'm aware of the time, I'll leave those conclusions up there and ask if we've got any time for questions.
Unfortunately, no. We need to move on to the lightning talks, but I'm sure we'll have plenty of time for discussion later after the lightning talks.